Section 3.3, Truth Tables for the Conditional and Biconditional. For the conditional statement, if P then Q, here's our general setup for two simple statements. And if we notice in the right-hand column, the conditional statement is always going to be true except when the antecedent is true and the consequent is false. In other words, a true to a false. All the other cases are going to be true. Let's do an example. Construct a truth table for the statement, if not P, then not Q. So I've got my standard four-case truth table. I'm going to start in column 1, and I'm going to negate the P values on the left-hand column under the P. And then I'm going to go over to the not Q column, negate the truth values under Q on the left side. And then remember, I'm looking for a true to a false. All the other cases will be true, and I see that in case number 3. All of the other cases are going to be true. So first case is a false to a false, which is true. A false to a true is a true to a false is false, and a true to a true is true. The biconditional, P if and only if Q, is saying the same thing as if P then Q and if Q then P. And in fact, if you construct a truth table for this compound statement here, you'll come up with the decision column right here, the answer column. And so we see that the biconditional is going to be true in two cases, when both simple statements are true or when both simple statements are false. So the way to think about that is if the simple statements have the same truth value, the biconditional will be true, otherwise it's false. And let's try an example shown here. And notice it is a biconditional. That's the last decision that we're going to make. So where are we going to start? We're going to start in the parentheses. Column number 1 is not Q, and this is 3 simple statements, so we've got 8 cases. So we're going to take everything in the Q column and negate it. And then we're going to move over here to the R column, and we're just going to move the R truth values over that we see on the left side. And then this is a good review of the conditional statement. Remember, this is going to be true everywhere except when we have a true to a false, which we see here in case number 4 and also in case number 8. All of the other cases are going to be true. So case number 4 is false, case number 8 is false. Now we're going to come out here for column number 4, which is not P. I'm going to negate the truth values in the P column on the left and put those here. Now I'm going to compare 3 to 4 with the biconditional. And remember, it's going to be true when they both have the same truth value. So if I look in case 1, I have a false and a true, so that's going to be false. If I look at case 2, I have a false and a true, that's also going to be false. Case number 3, again, I have a false and a true. Case number 4, I have a false and a false, so that's going to be true. Likewise for the next 3 instances, because I have true and true, true and true, true and true, and then the last case is going to be false because I have a true and a false. Let's use real data in compound statements here with conditionals and biconditionals. So we're going to use this graph that looks as the age grouping for State College of Florida students. And it shows in a pie graph or a pie chart the distribution of the ages and the percentages in each of the groups. So let's take a look at this first statement. If 44% of the college population is younger than 20, or, so it's a disjunction, 38% of the population is age 20 to 29, comma, so we're going to have some parentheses, then 8% of the population is age 30 to 39. So let's go ahead and pick our simple statements, P, Q, and R. We have 3 of them. So I can write the original statement. If I go back and look at the original statement, I can write it like this. If 44% of the population is younger than 20, or 38% is age 20 to 29, if then 8% is age 30 to 39. Now we want to figure out the truth value. So if we look at our graph, 44% is age younger than age 20. If I look at the graph, that's true. 38% is age 20 to 29. That's false because that should be 41%. And then 8% is age 30 to 39, and that's true. And then I'm going to put my truth values down here. So I've got a true or a false. And then my conditional goes to a true. So this is true. So a true to a true gives me a true. So the original statement is true. Now let's continue with the same graphic, but a different compound statement. 5% of the population is age 40 to 49, and, so I've got a conjunction, 5% of the population is age 50 and older, comma, if and only if, so this is a biconditional, 41% of the population is age 20 to 29. So again, I pick my three simple statements, and I'm going to write the original compound statement. 5% is age 40 to 49, and 5% is age 50 or older, parentheses, if and only if 41% is age 20 to 29. So now let's pick our truth values. 5% age 40 to 49, that's true. 5% age 50 and older, that's false. It would be 2%. 41% age 20 to 29, that's true. Put the truth values over here. So true and false is going to give me a false. Biconditional is only true when both simple statements have the same truth value, so this compound statement is false. A self-contradiction is a compound statement that's always false. In the truth value in the answer column, the last column of the truth table, if every answer value is every value there is false, then that's going to be a self-contradiction. So let's construct a truth table for this statement. And I've got it on the next page here, and some of the steps were left out, but you can do this one, a biconditional P if and only if Q. Remember, it's going to be true if both simple statements have the same truth value, which we see in case 1 and case 4. The other two cases are false. Over here, they've given you a little bit more detail. Again, a biconditional. We're looking for the same truth value, so we see that in case number 2 and case number 3, 1 and 4 are false. Now we're going to compare 1 and 4 with a conjunction, and so we have to have the same truth value for that to be true. We have to have two truths for that to be true, and we look down there and we see none of the cases have that. They're all falses, so this is a self-contradiction. It's a logically false statement. Every combination of simple statements P and Q leads to a false compound statement. A tautology is a compound statement that's always true. Every truth value in the answer column will be a true, and then we say it's a tautology. So we're going to construct a truth table for this compound statement. It's a conditional. And again, three simple statements here. They've done the work for you in the table. And if you notice in the last answer column under the conditional, they're all true. So this is a tautology, or it's a logically true statement. And an implication is a special type of tautology. It's a conditional statement that's a tautology. The consequent will be true whenever the antecedent is true. So determine whether this conditional statement is an implication. And we set up the truth table, and we see we have all truths here, so this is a tautology. It's also an implication. Construct a truth table for this statement. So we have parentheses, P if and only if Q. So if P, if and only if Q, then P. So we're going to do this table line by line. This is a conditional statement. So in the first row here, we've got an if and only if, and we've got the same truth value, so that's going to be true. Here we're going to take this true and compare it with a conditional to the P, so we have a true to a true, so that's also true. In the next one, the biconditional here is going to be false because they have opposite truth values. Now we have a false to a false on a conditional, that's true. Row number 3, we have opposite truth values, so the biconditional is false. And then we have a false to a true, which is true. And in the last case, we have the same truth value, so we have true to true, false to false, which gives us a true biconditional. And then we have a true now to a false, so the last case here is false.